Ladies and gentlemen, my name is Hanna Bogucka from Rimedo Labs, and today I'm going to present considerations on the security of future AI-based radio access networks. First, I'll introduce the concepts of ORAN and IRAN. Next, I'll overview the security issues of intelligent runs. Then I'll present some example methods, xApps and rApps for security in ORAN and IRANs, and conclusions will follow that. I believe that the concept of Open RAN is already widely known. It is based on two ideas: the disaggregation of RAN functionality from the underlying hardware, and the definition of functional RAN modules with interfaces, open interfaces. The essential ones are RAN intelligent controllers, the non-real-time and near-real-time RIC, which are the software platforms for applications called xApps and rApps. The concept of IRAN differs from ORAN mainly in goals, paradigms, and architecture. It aims to make networks even more adaptive and intelligent, fully automated, and autonomous. The architecture focuses on the intensive use of AI embedded in distributed unit, centralized unit, or even radio unit, and on new orchestrators for RAN and AI workloads. There are several key challenges and enablers of successful AI RAN. They include, on one hand, latency-sensitive RAN operations, and on the other, computationally demanding AI algorithms. One that I'm going to concentrate on is security and trust for AI models. In ORAN and IRAN, attack surface can classify various kinds of attacks depending on the place or domain of their occurrence. There are typical radio communication attacks, such as jamming, signaling storms, denial of service, man-in-the-middle, among others. There can be attacks on open interfaces, typical attacks on software and APIs. And on top of that, there can be attacks on embedded AI algorithms, such as poisoning, evasion, or inference attacks. Apart from the extended threat surface, ORAN and IRAN also create security opportunities. First of all, this architecture allows for running specialized xApps in near real-time RIC to continuously monitor and analyze security threats and protect RAN. It enables detection of threats much faster before they impact the entire network's operation. Moreover, xApps and rApps can be developed for specific types of threats, which can be detected closer to the place of their occurrence. Just to mention, an example xApps developed in Rimedo labs for jamming and signaling storm detection and mitigation. They showcase ORAN potential for anomaly detection. On the left-hand side, we can see UML, the algorithm for jamming detection and mitigation, using simple ML algorithm anomalies for channel quality indicator and the reference signal received power value for jamming detection are detected. And on the right-hand side, we have UML algorithm for a UML diagram for signaling storm detection, where dbScan algorithm is used to classify timing advance parameter to detect the source of signaling storm. Now I would like to focus on an example of rApp protecting ORAN and IRAN from typical attacks on AI, such as model poisoning or data poisoning. And my example is Federated Learning algorithm for spectrum sensing. FL is an iterative procedure that engages end devices or FL agents to build their machine learning models based on locally measured data. The local model parameters are then exchanged to or sent to the Federated Learning server to create one aggregated model, which is shared among the devices. Then the FL agents adjust the corporate model to their local data, and the process of training, exchanging models, and aggregating them is repeated. Poisoning attacks targeting a subset of FL agents can be launched by embedding a well-crafted sample to pollute the data or flip the data labels in the learning process. This way, an adversary may attack or the corporate model outcome. Defenses against poisoning attacks in federated learning can be roughly divided into output validation and robust learning. If we can detect the malicious agent, we can reject it from participation in the federated learning and ban from operating in the system. Let us consider a label flipping attack on the measured occupancy of 5G resource blocks. Two goals and the effects of such an attack can be formulated. The first, shown on the top, is the apparent increase in the resource blocks occupancy, resulting in the secondary user's resignation from using them, and consequently, the availability of resource blocks for the attackers. The second one at the bottom, the second type, is the apparent decrease in spectrum occupancy, causing secondary users to use the reader resources even though they are occupied. And this, of course, increases the interference with the primary user transmission. These two types of the attacks can be either random or coordinated. The random ones are presented on the left-hand side, the coordinated ones on the right-hand side. Coordinated attacks miming the correlation in time and frequency by encapsulating the areas of true labels. On this slide, we can see the impact of the attacks aimed at false increase in resource blocks occupancy. The probability of true positive resource blocks detection and false positive resource block detection are presented versus the number of the iterations of the algorithm, the federated learning algorithm, and versus the signal-to-noise ratio. This type of attack aims at increasing the false alarm rates, which can be seen here. This can be seen when the attacks are launched in the 5th and 10th iteration. The most harmful attack is the random one, increasing occupancy labels from the original 30 to 75%. On this slide, we can see the impact of the attacks aimed at false decrease in resource blocks occupancy. And this type of an attack aims at the decrease of true positive rates, the detection probability. We can observe that again in the 5th and in the 10th iteration when the attacks are launched. This time, the most harmful attack is the coordinated one. The decreasing occupancy labels from the original 30 to 16%. And this is the UML diagram of the attack detection and mitigation rApp. In the first step, the statistical tests are applied to the model's kernel's weights. And this is the Kolmogorov-Smirnov test, reflecting the similarity of probability distributions. Then the models are classified as the ones that are alike and the ones that are outliers, and the outliers are considered as attackers and are rejected from the federated learning algorithm. The defense algorithm results depend on the type of the attack, and that can be summarized as follows. For the attacks aimed at the false increase in video resource blocks occupancy through positive detection of the attacks, the attackers is from 90 to 100%, and the probability of the false alarm is from 0 to 5% for SNR equal to 20 dBs. For the attacks aimed at the false decrease in RBS occupancy, the probability of true positive detection of the attackers is from 50 to 90% for SNR equal to 20 dBs, and from 0 to 10% for the same SNR. The key observations are that the attacks that cause more damage are usually harder to detect, and that the coordinated attacks with a lower number of fake labels are better camouflaged in the data labels. They mimic the true occupancy better and are harder to detect. The opposite happens for the higher number of flipped labels. Here we can see the results of the actual federated learning spectrum sensing algorithm after applying the defense methods. And we can see that for the attacks aimed at the false increase of resource blocks occupancy on the left, the false alarm of resource block detection is significantly reduced as opposed to the figures I showed before. And for the attacks aimed at the false decrease in video resource blocks occupancy, on the right-hand side, the true positive detection rate is increased to the level of fully secured system. Let me now conclude my talk by saying that openness and intelligence of future runs create both opportunities and challenges. And that AI/ML enables intelligence for greater security, but may be also the subject of the attacks. And therefore, the best practices for ORAN and IRAN security should incorporate a zero-trust model to monitor the networks, its components, and interfaces continuously, and that the AI algorithm protection mechanism should be also in place. Finally, let me mention some of our recent papers that discuss these topics in greater detail in IEEE Journal on Selected Areas in Communications and IEEE Communications Magazine. And I would also like to acknowledge my co-authors from Rimedo. I also encourage you to read my blog posts on ORAN security, and thank you very much for your attention, and I will welcome your questions. Thank you.